What's up, people? I want to talk to you about a couple of different problems. These are on your sheet of reviewers, um, and they look similar in that they're both objects hanging from strings and accelerating systems. But there's a big difference, and the difference illustrates a great point of why we do things we do. And I mean analytically, why we take some steps that we take towards, when we solve problems, okay? So in this case, a train car is accelerating to the right, all right? And what we end up with, I'll exaggerate, is this string, this mass hanging from a string, all right? The real angle is a lot smaller, right? It's like that and that, but I'll exaggerate the angle a little bit. Okay? And let's see. Now the other one, what I'm gonna do, at the risk of screwing people up, is this, because it's gonna look the same. This one is also an object hanging from a string with a T and an mg. All right. Now the question is, even though these free body diagrams are the same, should we handle these two problems the same way? All right. Item 1 over here is that's the whole free body diagram. Some people want to say, well, it's pulled this way, or else how could that string be at an angle? Well, the string is at an angle because of what the object is doing. The object, if you break T into the correct components, you'll see why this object is accelerating, all right? Or what makes it accelerate. Now, the deal with this is it's the most appropriate to break this one up into Ty and Tx. All right, there's the whole free body diagram. And you'll notice that this says well, this thing accelerates horizontally because of that x component of the tension force. All right? The rope isn't, it's not that the object is pulled out this way and that's why the string looks like that. That's not the case at all. It's the object's inertia that tries to keep it where it was, and so when the train starts accelerating this way, well, the object wants to, maintain what it was doing before, and so, well, that's where the angle in that string comes from. Okay. So there's one net force statement we could write, right? Now, it happens to be that the angle is here in this one, so this is actually going to be T sine theta equals MAX, right? And then we could also say, well, it is accelerating horizontally, but it's not accelerating vertically, so we could just say that Ty minus mg is 0, or T cosine theta equals mg. All right, so we could use that. We could use, these two equations to, figure out stuff about that object's motion. Okay. Now, this one over here is different. All right, and the big difference is, we got to talk about why is it that we break T into components. In the most general sense, why is it that if there's an object on the, on a horizontal surface here, and it's being pulled like that, why is it that we break T into components? Why bother? All right, and the answer is because what we really always want to do, we don't always write it this way, is we always want to really do this. Oops. Yeah, fine. We always want to look at components of forces that are parallel to acceleration. right, and components of forces that are perpendicular to acceleration. So the only direction an object on a horizontal surface, the vast, vast majority of the time, the only direction it would ever accelerate is horizontally, all right? So we look at components of t that are parallel to that acceleration. It just happens to be in the x direction, right? And that's the whole reason that, why did we break, when we get into this case, why do we break mg into components that look like this? Well, because this component is parallel to the direction this thing might accelerate. And this component is perpendicular to the direction the thing might accelerate. So the big question you have to ask yourself when trying to figure out which thing to break up into components is, what direction does the object accelerate? What direction does the object accelerate? You know, we're given that right here. It accelerates horizontally. So that means we break things that aren't horizontal or vertical up into horizontal and vertical components. And here, t gets broken up into tx and ty, which we really could, if you want, call kind of t parallel to acceleration, t perpendicular to acceleration. Okay? So over here, the question is, what direction does this object, this mass, accelerate? Well, this one does not accelerate this way. It accelerates down an incline with the car. So therefore, the force that is not on one of these axes is mg. And it makes sense here to do the components of the force that aren't parallel. Oh, sorry. It makes sense to draw components of the force that's off axis. So since t is already perpendicular to the direction of acceleration, don't monkey with it. Monkey with the force that is not parallel or perpendicular and break it up into components that are parallel and perpendicular. So here we have, well, mg parallel equals ma. And if this is our angle theta, there's our angle theta. This is mg sine theta. And then we could say that t is mg perpendicular, or t is mg cosine theta.
Hey, Coach, how you doing?
Hey.
Can I get the lacrosse papers? I didn't miss the meeting.
And again, I don't know what the question asks, but I don't know what the question asks in either of these cases. But the nice thing is that who cares what the question asks? This is how you're going to solve it, right? I mean, without even knowing what they want to know, you know, do that, right? I didn't write in here that I'm doing this. Net force in the y equals may. So if you don't know how to solve a problem, if you don't even know what it's asking, if you lose the ability to read in the middle of a question, just draw a free body diagram and write net force statements, and I guarantee you'll get going in the right direction. Okay. But yeah, in review here, the deal is this: break. Oh boy, it's the best way to say this. Break off axis forces into components. Hang on. That are parallel and perpendicular to direction, whoops, off axis, to direction of acceleration. All right, that's the big deal. How do you know? Come here. How do you know which force to break up? If there's a question, here's how you know. Figure out what direction the object in question accelerates in. All right. And anything that's not in that direction or perpendicular to it, break it into components that are parallel and perpendicular to it. Okay? Hope that leads at least a little bit to some help with these two problems and in a more general sense to any problem where things are at angles. Okay? See you folks.